Welcome to the Explainer. So, have you ever wondered how we actually learn from our mistakes in real time? I mean, we do it all the time, right? Well, today we're exploring an absolutely fascinating frontier in artificial intelligence where machines are doing exactly that. They're learning directly from their own experiences and adapting to totally dynamic environments, all to maximize their rewards. We are looking at the literal heart of modern reinforcement learning, temporal difference learning, or just TD learning for short.
Okay, let's dive into this. Think about that question for a second. In our own lives, you don't usually wait until the very end of a long road trip to realize you missed an exit, right? You adapt in real time. And honestly, this is the core superpower of TD learning. It lets an artificial agent refine its predictions and learn from its mistakes step by step, literally before the task is even complete. It's a total game changer.
Here's our roadmap for the Explainer today. We're going to meet the core concept of TD learning, use a maze analogy to see it in action, figure out why it's a better way to learn, check out a few of its variants, see how it's used in the real world, and then finally, peer into the future of AI.
All right, Section 1, meet temporal difference learning. So what is it? Well, temporal difference learning is basically a method of predicting future outcomes by learning on the fly. Now, unlike supervised learning, where you have to spoon-feed the AI massive data sets that have been painstakingly labeled by humans, TD learning lets an agent learn directly from raw interaction with its environment. It's all about constantly updating an estimate of the value of a specific state, which we mathematically denote as V of S. Basically, it evaluates a situation, makes a move, and then instantly refines its expectations based on what just happened. No waiting around to see how the whole sequence ends.
Moving right along to Section 2, escaping the maze.
Imagine an AI agent as a hero trying to navigate a totally dark, unknown maze. It doesn't have a map, it has no idea where the prize is. As our hero moves forward, it receives immediate feedback. Maybe it finds a tiny reward, or, maybe it bonks its head on a dead end, a pretty clear penalty. Now, step 3 is where the absolute magic happens. Instead of waiting until it miraculously escapes, or fails completely, to learn anything at all, the agent updates its expectation of that specific position's value incrementally, right then and there.
Section 3, a better way to learn. You see, TD learning is essentially a versatile hybrid. It combines the absolute best of two older, much more rigid methods. On one hand, you have dynamic programming, which is super demanding. It needs a complete model, basically a perfect map of the environment with all the probabilities already calculated. On the other hand, you have Monte Carlo methods. These don't need a map, but they have a massive flaw. They have to sit around and wait until the entire episode finishes before they can update their estimates. TD learning brilliantly bridges this gap. It's model-free, so no pre-programmed map is needed, and it learns incrementally after every single step.
Now, what's really interesting here is this equation. Let's translate this elegant math into plain English. This is the TD0 equation. That V of ST, that's your current expectation. You update it by adding a fraction of the new information you just gathered. The alpha symbol represents the learning rate. You can think of it as how stubborn, or alternatively, how open-minded the AI is to changing its beliefs. And that gamma symbol? That's the discount factor. It simply weighs how much the AI cares about long-term future rewards versus, say, instant gratification.
The real heartbeat of that previous equation, though, is the temporal difference error, or delta T. This formula simply measures the gap between what the agent expected to happen and what actually went down. If the TD error is a positive number, well, it means the outcome was an unexpectedly pleasant surprise. So the agent increases its estimate of that state's value. But if it's scratch that. If it's a negative number, it's a disappointment, which triggers a downward adjustment. This continuous on-the-fly feedback loop is exactly how machines refine their predictions over time. All right, let's jump to Section 4, variants of TD learning. First up, we have TD Lambda, which introduces something incredibly clever called eligibility traces. Imagine taking 50 steps in our maze and finally finding a piece of cheese. Which of those 50 steps actually deserves the credit? Eligibility traces solve this puzzle by assigning credit based on temporal proximity. Basically, the most recent steps get the most credit, and the credit decays the further back in time you go. That lambda parameter controls the decay, effectively bridging the gap between a single-step update and a full Monte Carlo-style historical update. So the crucial point is how these variants apply to different types of learning, like SARSA and Q learning. Both extend TD learning to evaluate specific actions, not just general states. SARSA is what we call on policy. It evaluates the exact and sometimes pretty flawed path the agent is currently walking. Q learning, however, it's off policy. It's a bit of a rebel. It mathematically calculates the absolute optimal path, even if the agent is just wandering around exploring randomly. This makes Q learning incredibly effective when your exploration strategy is totally different from your ultimate goal. Next up, Section 5, AI in the real world.
These algorithms aren't just theory, they are literally everywhere. Back in the 1990s, a system called TD Gammon completely shocked the world by mastering backgammon purely through self-play. In robotics today, TD learning controls adaptive navigation, allowing machines to adjust to wildly dynamic environments without hard-coded instructions. In finance, it's used to predict future returns from partial information to guide sequential trading. And in healthcare, it's even being applied to evaluate long-term outcomes to plan optimal treatments for chronic diseases.
But hey, developers still face some really exciting puzzles to solve. Stability is a massive one. When TD learning is combined with complex approximations, the math can actually diverge and break down. Then there's the classic exploration versus exploitation dilemma. How do you mathematically balance exploring unknown, potentially better states against exploiting the rewards you already know are there? And finally, even with those eligibility traces we talked about, accurately assigning credit across incredibly long sequences with delayed rewards remains super tricky. Finally, let's wrap up with Section 6, the future of AI. And this brilliantly illustrates where the field is at today: deep reinforcement learning. By fusing the step-by-step updates of TD methods with the massive pattern recognition power of neural networks, systems can now handle insanely high-dimensional data. We're talking raw video pixels or complex sensor data. Powerhouses like DeepQ networks and AlphaZero, they rely heavily on TD learning to update their value functions within some of the most complex environments imaginable. Which leaves us with this final thought. Temporal difference learning really isn't just an algorithm. It strongly mirrors how we humans learn from the subtle shifts and differences in our daily lives, adjusting our expectations step by step. As these machines learn not just from their final epic successes or failures, but from the granular, messy journey along the way, how close are we getting to truly experience-driven intelligence? It is a fascinating frontier, and TD learning is the engine driving us there. Thanks so much for joining me for this explainer, and keep learning.